We'll wait for 2 minutes and then we'll start. So I'll begin, and if other people are joining, they can join subsequently. So I hope the screen is visible. Welcome to yet another problem solving session for the course Geographic Information Systems. The instructor for this course is Professor A.K. Saraf from IIT Roorkee, and I'm the teaching assistant Anshana from IIT Kanpur. So, we'll be discussing the week 4 lectures primarily, focusing on the uh, pre processing methods and as well as the interpolation part. I might not begin the GIS analysis part for this session because it's mostly a part of week 5. So, we'll do that in the upcoming Tuesday session. Okay, so yeah, we'll start. So there are different GIS analytical operations and which are primarily like the basic functions are involve the area and distance measurements as well as buffer generation. Now the buffer generation part we won't be discussing in much detail, so we'll be just uh, kind of recapping or reviewing the area and distance measurement part today. So I hope you have already gone through the lecture. So I'm just summarizing all the topics here, which I felt a bit necessary before going to the problem solving part. So this area and distance measurement, as I said, it can be done manually or it can be done by auto population in the attribute table. So if you are familiar, 1 second, I'll just. Okay. So if you have used any of the GIS software, you might be familiar with this attribute table, or else we have already discussed the different type of data like spatial data and non-spatial data. So the attribute data is a type of non-spatial data, which includes all the details about uh, like area, the length, all those details can be stored in the attribute table of a particular map, or something that you have, some information that you have put in the GIS software. So there are different types of area and distance measurement. Like we can do it in different ways. So the the few ones we'll be discussing here, and which already professor has also discussed in the lecture. So we'll be just touching upon those topics. So the planar measurement type is the, like, we can have one kind of measurement, that is the planar measurement, and then we have the geodesic measurement. So planar measurement is like, it's basically like you're doing the measurement in 2D. Okay, planar. So it is like XY plane, or if you are familiar with this, like XY plane, YZ plane, or ZX plane. So it's like two-dimensional, only 2D. So it involves doing the measurements in 2D. Like for example, if you have seen the survey topo sheets, like especially for GSI and all, they have these topo sheets which uh, gives information about the kind of terrain that it is, the contour, like how, what kind of elevation uh, is in that region, what kind of terrain, like what kind of rocks are there, minerals are there. So topo sheets contain such information, especially regarding the topography of that area. So the survey topo sheets or any other map which are in 2D system, that in that we can calculate the area, the even the perimeter or distances very easily. So generally all area measurements calculated are in planar. So it's basically like, for example, if you have an image like this, so this area we will be calculating, and this will be done in a planar manner, like 2D kind of thing. Of course it might have a three-dimensional aspect, but that we will not consider. So we will just look at the this part, not the elevation part or depression part. We will just cover the area part. But when we go for 3D, that is like in geodesic measurements, then it becomes a little complicated. So what happens here is, like for example, if you have a hilly terrain, if somebody like is using a DEM model, like you're familiar with the digital elevation model, right? So if somebody is using the DEM model, or even like some kind of satellite image, then we have to be very careful with the area measurement, because here we are also considering the three-dimensional aspect. Okay, so the shortest line between any two points on the Earth's surface on a spheroid or the ellipsoid. So because the Earth's surface, we don't consider it as an absolute sphere. It's not a very good drawing, but still, Earth we consider it as a more of an ellipsoid. So not exactly like this, but little flattened on top and then bulged on the sides. So the shortest distance, or the shortest line that you can draw on the Earth's surface on a spheroid is considered in this case. One use for a geodesic line is when you want to determine the shortest distance between two cities for an airplane's flight path. So if you have traveled in a big airplane, or even if you have seen some videos regarding that, so we see certain monitors in front of the seat, especially if it is a long distance international travel or something, long duration travel. So then in front of the seat they will be showing the kind of, just like how you have the Google map for your on road map or something. So similarly you have for the airplane. So it sort of shows the different places and where the airplane is moving, like how it is going, where it is right now. So such things, it's based on this geodesic measurement. Okay. Then another type is the like loxodrome and the great elliptic method. So a loxodrome is not the shortest distance, because geodesic we were considering the shortest distance. But in loxodrome, it is not the shortest distance between 2 points, but instead defines the line of constant bearing or azimuth. So what happens is, instead of going through a curve, so instead of going through a curve, if it is in a straight line, many of such distances are used mainly for aircrafts or other things, or even for missiles and all, we use this loxodrome thing. Okay. So, if the distance is too large, that means the curvature of the earth will play a very important role. And like what kind of projection system you are using, or what kind of input map you are using. So, in such situations, we will consider this one rather than the geodesic. Great circle routes are often broken into a series of loxodromes, which simplifies navigation. Because see, if it is on the ground, then we don't need this method, because it's like, it's a little too complicated. But this is required in case of navigation, especially aerial navigation, like in case of uh, airplanes, or in case of missiles. We use this loxodrome method. Even the geodesic we can use for aeroplanes and all, but when you cover a longer distance, when the curvature is more, has to be considered more, because if it's a short distance, like for instance, let's say if this is the surface, okay, here we have the curvature. If it is from here to here, it's more or less a little straight, not that curved. But if I have to move from this point to this point, the curvature is very well, has to be taken into consideration. Okay. So in case of great elliptic, the line on a spheroid or ellipsoid defined by the intersection at the surface by a plane that passes through the center of the spheroid and the start and end points of a segment. This is also known as a great circle when a sphere is used. It's basically, how can I say, let me see if I can get some image. I forgot to include in this. Just a moment. So, instead of an ellipsoid, I'll try to show the simplified version in a sphere. So, let's consider this sphere, okay? So, in this case, the instead of ellipse, we'll be having a circle. So, it's basically this sphere into, like, if you cut it like this, you're getting a circle over here, right? So that's what, it's a great circle. This is known as a great circle. So multiple such circles are composing this entire sphere. Okay. In case of ellipsoid, or like we have a great ellipse or elliptic measurement. Then there was a discussion on the aspect direction measurement. So basically the aspect it represents the direction a surface faces by identifying the steepest downslope direction from each cell to its neighbors. So what it is essentially telling you is that, like, if you, for example, if we have a grid image, okay. So this is a grid. There's some problem with my computer, so there is a little bit of lag. So please bear with me. Okay, so we have a grid like this, and each grid will have different values. Okay, so suppose this grid is representing an area which has some elevation or depression, whatever it is. So the aspect will represent the direction a surface faces by identifying the steepest downslope. So for example, let's say we have some a terrain like this, and this is the steepest downslope. So this steepest downslope direction from each cell to its neighbors will be uh, determined by the aspect. So it is essentially the slope direction, in which direction that slope is there. Okay. The output raster values indicate the compass direction the surface faces at each location. So it will be, this aspect direction will always be measured in 0 to 360 degree, where 0 and 360 will represent north. For example, like if you consider a compass like this, so this will be 0 degree and this will also be 360 degree. Okay, like if you divide it like this, so this is 0 degree, this is 360 degree, this is 90 degree, this is 180, this is 270, like that. So it varies from 0 to 360 degree. Flat areas with no downslope direction are assigned a null or a special value. Like for instance, we are only talking primarily about the terrain which has some kind of slope. So if in this particular image, or which we have like represented in terms of grids, for instance, if you have flat areas, uh, like if you have a DEM model in which there are elevations, there are depressions, and at the same time there are flat terrains, those flat regions will not have any particular number. Rather, it will be either assigned as null or some other value which signifies that this is a flat terrain. Now, this slope measurement is yet another important parameter. So, slope is the maximum rate of change between each cell and its neighbors. For example, the steepest downhill descent for the cell. Now, you don't have to go into this too much technical details, but rather like common knowledge is there, like what slope is, right? So like in your house, or like you're driving on a road, so you come in a region where there is an elevation, there is a downslope direction, all those things. So that is something you have to keep in your mind. Now technically it is the maximum rate of change between each cell and its neighbors. So like the slope value will vary. Okay, so same thing, like you have grids like this, and then between each cell there will be a variation. Like for instance, if this is 4 and let's say this is 10, so that steepest that kind of change, maximum rate of change between each cell, that is the slope. Now every cell in the output raster will have a slope value, and the lower the slope value, the flatter the terrain, which means like here I'm just randomly assigning some number. So for instance, here I've put 4, here I've put it as 10. So 4 implies that this region is kind of flatter when compared to this region. So it's kind of relative. It's not an absolute value, but it's more or less a relative thing. So this 10 is more steeper and 4 is more flatter. The output slope raster can be calculated as percent of slope or degree of slope. So it's kind of, as I said, you don't have an absolute value. How that grid cell value is varying with respect to its adjacent cells or neighboring cells. According to that, the slope measurement is accounted for. Now we'll be looking on the pre-processing of spatial data sets. Okay, so just a moment. So it's essentially like pre-processing is kind of like you have a spatial database. So you're preparing that spatial database for real analysis. Like the ultimate thing that you're doing with GIS is like you're creating some kind of model with a lot of data input, which kind of represents the real world scenario, right? So you have a lot of spatial data available with you. So first of all, you cannot just use that data as such, like how you have got it, because you might have to combine multiple data, you might have to like remove certain things. So for such purpose, a pre-processing is necessary. So it's kind of equivalent to like a primary step, you can say, before you are doing the proper processing or real analysis that will be done with these data sets. So pre-processing involves all these steps. So you can do format conversion. So it's basically like, for instance, if you have a data which is in analog format, okay, but if you have to use it in a computer, then you need to convert it into digital format. So I'm just giving few examples to say what each of these means. So analog to digital conversion, or for instance, uh, you might be familiar with the TIFF format. So sometimes TIFF itself will be converted to GeoTIFF, where you already also have the geographic information. Then we have the data reduction and generalization. So one more thing, I'm not like, now they are not showing any kind of warning, but if this meeting like is restricted to 1 hour, in that case, before it gets over, I'll put on another link in the chat so that you can join back again, because I have been facing this problem in the last few sessions. So because of that, sometimes within 1 hour this might get closed automatically. So before it happens, I'll put another link in the chat box so that you can rejoin as soon as this meeting ends. So as I was saying, the next one is the data reduction and generalization. So data reduction does not necessarily mean that we will delete the data. Like, data is not removed as such, but it means like we will do some repetition checks. Like we were talking about redundancy, right, for compression. So if there are repetitiveness in the data, or like basically we'll be like, we don't need a lot of unnecessary things within the data. Like if the data is repeating, or if some point is having too much of information, that we can actually generalize. So that is why we are doing data reduction and generalization. We are not as such removing the data, but more or less we are combining it, merging it, or like according to our requirement. Then we have error detection and editing. So each step, like sir was also mentioning this, whenever you're working with GIS, at each step you will have to check for errors. So because you're working with such huge data sets, it's not like very small thing. Most of the time you're working with satellite images or something of such sort. So that contains a lot of like information, and then it's very big files are involved. So it's always better, like at every step, like pre-processing, processing, whatever it is, at every step you have to check for errors. Error detection is very much important. Okay, so if any error you have found, like some point, like for instance you were finding some points and some points were wrong, something like that, then you can just remove those. Like you can edit those, put the correct ones, and then do the further things. So check for the errors, edit it if you find something, and then move on to the next step. Then we have this merging is involved. Then we have the edge matching. Like merging is basically combining the data, whatever is there. Okay. Then that we'll be discussing in detail all these things, but then I'm just touching upon each of the topics. Then we have edge matching. So like for instance, if you have, I think I have an image also for this. Anyway, I'll just tell you something. Like if you have a topo sheet, something like this, okay, then you have another one like this. So you're basically trying to match these edges, okay. So if you're having two edges in topo sheets data, then sometimes because of the projection problems, like what happens is that if you remember, like whenever we are doing georeferencing or something, or like there are different projection methods involved. So when you do the projection, at times it might not come accurately as you might have desired, because you might not have given the GCPs properly, or some information might have caused some distortion in this. So the edges will not fit properly. So that edge matching needs to be done. So we might have to do it manually rather than doing it automatically. Then we need to do the rectification, registration, and georeferencing that we have discussed in the georeferencing part also. Then we will be doing interpolation. Like interpolation is basically you might have some data. It's not like you are looking at a huge area and you go to every nook and corner of that area and collect data, right? It's not possible. So you might have some data from the area which you can interpolate and consider for the entire region. This also we'll be discussing, so you don't have to worry about that. Like sir has also discussed, and we'll also discuss about this. Then we have the image or photo interpretation. So generalization, like we have talked about it over here, right? Data reduction and generalization. So generalization is the process of simplifying complex spatial data, but it's not always straightforward because there are no fixed rules to follow. This is mainly like, it's up to the person, like the person who is doing it, the people, like based on the requirement, user requirement, based on the person who is doing this generalization. So it requires judgment and decision making, which is based on the situation and the requirement for that particular data set. So in order to do it effectively, we need to know why, when, and how to generalize the data. Like why are you generalizing the data? Like at times redundancy might be there, like repetition of data might be there. That could be a reason. And when or where you should do it, that is important. How you are going to do it, that is also important. So there are different techniques used for generalization, and each of it has different accuracy, speed, and complexity. So it's all depending on what your requirement is. Always that is the thing. So data generalization also has different types. So like we have aggregate points, we have aggregate polygons, collapsed dwell lines to center line, collapsed road detail. So it's like basically aggregate points is it creates polygon features around clusters of proximate point features. It's basically if you have gone through the lecture, you might have seen this Thesan polygon. So it's like you have one point which is sort of representing this points which are there in this polygon. So similarly you might have something like this, then you might have something like this. So these points are basically the aggregate points. So creates polygon features around clusters of proximate point features. Then we have aggregate polygons. It combines polygons within a specified distance of each other into new polygons. So again, it's like how we have generalized the point. Similarly, we'll generalize the polygons also, and then consider one polygon. So similarly, so we are aggregating it. Then we have collapsed dwell lines to center line. So in this, it is like a dwell line for a railway track or something like that. So in such case, you can merge into one line or drive a central line from the dwell line. So it's like you have two lines. Either you can merge this and consider it as a single line, or you can just through the center you can consider another line which is representative of these two, like some equidistant line or something like that. So this is basically a generalization. It's not like these two lines are absent, but we are more or less generalizing it. Then collapse road detail. So it collapses small open configurations of road segments that interrupt the general trend of a road network. Like you might have a traffic circle. So for example, we'll replace that with a simplified depiction. Like we won't go to the intricate details. Like you might have a traffic circle, but when you're representing it, you might not be giving much importance to that. Rather, we'll be generalizing it. Then we have this delineate of built up areas. So built up areas is basically unused open lands might be there in a region. Such region we'll consider it as built up areas. So that in that we'll create polygons to represent built up areas by delineating densely clustered arrangements of buildings on small scale maps. Then we have the cartographic partitions. So here it creates a mesh of polygon features that cover the input feature. Then we have the merge divided road. So it generates a single line road features in place of, it's basically what I discussed earlier also, but then you have these different types present. Then simplifying the building simplifies the boundary or uh, footprints of building polygons while maintaining their essential shape and size. This essentially it is more I have personally done this in another software, not in actually ArcGIS, but we had done this image classification and all. So in that case, like if you're given an image of a region where you have buildings present, you might have a forested area present, you might have a water body present, road present. So all these things. So we'll be representing it in terms of polygons, polylines, and points. So such generalization can be done. Again, other types include simplifying it in line format, polygon, smooth line, smooth polygon, thin road network. So simplify line is basically simplifies the lines by removing extraneous bends while preserving the essential shape. Like for instance, let's say we have something like this. So these bends are not very prominent. So we can actually just smooth it out, which is a little more representative of this feature, but rather a generalized one. Okay. Then simplifies polygon. Again, in case of polygon also, unnecessary bends and so small things that we can just remove and create a much generalized shape. Then we have smooth, sharp angles in lines to improve the aesthetic or cartographic quality. Thin road network, it generates a simplified road network that retains connectivity and general character for display at a smaller scale. So the essential thing that you have to understand is, like I just put these examples here, but the bottom line is in data generalization, you're not actually deleting much of the data or anything, but rather you are just averaging it out or aggregating it so that you don't get confused. Like if general information is all that you need, you don't need to go into much of the details, then there is it's not very like, for instance, as I said, like if you have an image and your purpose is to classify it in terms of let's say vegetation, buildings, agriculture, something like that. So you don't have to focus on each and every building in this case. You just need to generalize it. Okay, here we have the buildings, that's it. Nothing more than that. So in such cases where that intricate details are not required, we can do data generalization. Then this image merging and fusion was discussed a little in detail, so we'll be talking about that. I think there is a lag in me talking and the slide shifting, so I think that's a problem with my laptop, so please excuse me for this. So in case of image merging or fusion, multi-sensor image fusion is the process of combining relevant information from two or more images into a single image. Like you might have two images, and like one image might be containing some particular detail, the other image might be containing another thing in much more detail. So if you combine both the images, you will get a wholesome idea of that particular region or whatever it is, like what that image is about. You will get a wholesome idea. The resulting image will be more informative than any of the input images. So in case of remote sensing application, the increasing availability of space-borne sensors provides opportunities for different image fusion techniques. Several applications require high spatial and high spectral resolution in a single image. This is mainly like in case of satellite images and all. So you have different kind of images that you get, like you may have like panchromatic image, you might have a multispectral image, you might have a hyperspectral image. So it like that is completely dependent on its spatial and spectral resolution. So depending on your requirement, you can take the images accordingly. You can just merge them and get the details out of it. So whatever we do in this image, like what this emerging or fusion, the result will be more informative than the individual input image. So the example, or like why this is needed, if you think about it, it's like if you have two different resolution images, okay, uh, of the same area, like wherever you are staying, your house area or something like that. So you have two different images, like resolution images, and it's almost taken at the same time. So in that case, individually they may not be very useful, but if you combine it, you might get some information out of it. So this high spectral, or like high spatial, high spectral we were talking about. So this high spectral is basically uh, more narrow bands. Like you might be familiar with this electromagnetic spectrum, right? So in that electromagnetic band, there are more narrow bands available, and more number of bands, that more the number of bands, higher spectral resolution it will be. So image fusion techniques will allow the integration of different information sources, like it's basically what I said. So the fused image can have complementary spatial and spectral characteristics. Okay. In satellite imaging, we have two types of images available. We have the panchromatic image, which has high spatial resolution, and the multispectral image, which has coarser resolution. So panchromatic is quite common. That is like the black and white image that we get. Multispectral and hyperspectral are more colorful, but then panchromatic is like black and white. So generally, this panchromatic is merged with this multispectral to convey more information, because this gives you more information. This panchromatic image gives more information in terms of spatial resolution, like more space, like in that space you get more information. But then multispectral cannot be taken for the into consideration for the high spatial resolution, but it's more like high spectral resolution it has. So here you can see this image. So this is the panchromatic image, that is IRS 1C pan image. So this one that you see here, and then you have this LIS image, okay, LIS 3 image. Like these are all satellite images, okay. So this is black and white in color, and this is like false color composite, like RGB, like it's more red and green in nature. So if you take a look at the resolution, so this has a resolution of 23.5 meter, and then this has a resolution of 5.8 meter. And now when you merge these two, you will get an image something like this. Now this one will have a high spatial resolution, and along with that you are also getting colors. In this case you are not able to identify much of the things. Here it's a little more like you can classify the things what are present and all. But here it's not very evident, like you can see but then it's not very clear. But when you combine both these images, you are getting this high spatial resolution also, and at the same time you can see this different colors and representing different features. So I didn't include the zoomed in image which sir has shown, but essentially like if you take a look at this, just like aerial view or something. So not like what I'm trying to say is, in this one you have more information. In this you don't have that much of information. So in this, like I don't know which part they have zoomed. Let me just check it. I think it is this region. Hmm. Sir has provided an image in which he had zoomed. Oh, let me change the color so you can see. Okay. I believe it is this portion. So this is a uh, portion of the Delhi golf course. Okay. And I think the corresponding part will be over here. Yeah, this one. So if you take a look at this image, and then we have this one. I should have included the zoomed in image. I forgot to include that. Basically what I'm trying to say is, in this when you combine these two and you're getting this, much of a difference is not very noticeable. But then if you zoom in, especially this area which was mentioned to be the golf course, so in this image, because of the pan image, we are able to see the inducible holes that are present in the golf course. So the merged image will contain that information also, because the FCC image was not giving that information. So that is one benefit of image merging or fusion. So here we have earthquakes where the color transformation was done. So here we have the false color composite images. So we have the pre-earthquake image, we have the of 2000, 14 November 2000, then we have the 27 October 2005. So it's like 5-year time span gap is there, and then this is the output that you're getting. So that time variation also can be accounted for. Then another part of this pre-processing was edge matching. Okay, so this, like, briefly we'll be discussing this. It'll depend basically how best two data sets are available. So what their quality is and the time difference. All those things should be very minimum. Like quality should be good. Time difference should be minimum. Okay, so if you have two survey topo sheets present, like one is belonging to, let's say, in the 70s, and like this is an example that Sir has mentioned, so I'm repeating it again. So, like one belongs to, say, 1970, something like that, and then the other topo sheet is of 2020. Okay, now there might be a difference at the edges, which maybe like little different from the map projections that were used at the time, like in 1970s, and which is used in like 2020. So that time difference might cause some mismatch, but then to some extent you might be able to join these two. Like if this is of one time period and this is of another time period, definitely there might be some variations, right, over that duration. Like let's say if this is like in 2010, okay, and then this was taken in, like, say, 2020, so 10-year gap was there. So there might be difference at the edges, which we'll notice significantly because of maybe like different map projections. uh, there will be some mismatch, but then you can to some extent combine them. And this is mostly better done, like better efficiently done, if you're doing it manually rather than doing it automatically. Is the screen sharing working? I just saw the message only now. You can just reply me in the chat so I can understand. Okay, thank you. I didn't see the message, sorry. I'm just summarizing the topics because I'm not touching upon every little thing that Sir has discussed. So if you want me to specifically discuss a topic or something, you can put it in the chat. So then I can focus on that, because there is a lot of information in this week 4 lecture, and in 2 hours it's not possible to complete it, and plus the problem solving. So that's why I just picked some topics and I was discussing that. So if you want me to discuss something else which you didn't understand or something like that, you can put it in the chat. Okay, this is yet another example of edge matching which is done in ArcGIS. So here there is this gap that you have seen, right, between two polygons. So this was done in ArcGIS. So click the edge that needs to be aligned. Here we have done. Click the edge to which the first edge should be aligned. So one edge we chose, then which should be combined with this. So we have to select that. So we'll be selecting this. Okay, so the first edge is adjusted to match the second edge which filled in the gap. But at times it won't be so easy. At times this gap might be a little complicated. The edge might not be very easy to match. So you have to choose the point very carefully. One session, like before this, like we have this 12-week sessions, right? So in one session I'll exclusively dedicated to showing you all these things in GIS. Why I'm not including it right now is because we have a lot of topics to cover, and then problem solving needs to be done, so it might be a little time consuming. So I thought I can combine everything maybe and then show you one project or something. So I'm trying to do that. But if you feel like, oh, just this theory is confusing, then feel free to tell me. Then I'll try to maybe include a screen recording, or I'll try to do it as like along with these sessions. Okay, so that is regarding edge matching. Now we will be discussing about spatial interpolation. So we'll be discussing about the spatial interpolation techniques, and it's very important to create continuous data from the vector data. Vector is more or less discrete, so we need to do spatial interpolation in order to generate the continuous data. Even this can be done from polylines also. It's not just about points. Even from polylines we can create surface or continuous data. So in this case, what exactly is spatial interpolation? So interpolation is something like you have, let's say, change the color so it's more clear. Okay, so we have one point over here. Okay, we have another point over here, maybe another point over here. Now I need the information between these 2 points, or let's say these 2 points. So between whatever information or points I need to generate, that is what you basically do in case of interpolation. So what spatial interpolation does is it will turn raw data into useful information. You will get you might be having some random 2 points or 3 points, whatever it is. When you interpolate, you might get more better information out of it. So more more the number of points, the better it is. Like if you are familiar with these mathematical plots or something like that, so you know that it's always better, like if you just have 2 points and you are joining it, that is not very accurate, that will not give you much of information. So it's always better to have at least 3 points. So similarly, in this case also, more the number of points, I'm not saying like you need every single point in that region or information on that, but rather like instead of 3 points, like let's say if you have information from some 5 points or something, then that is easier, or that will give you, when you do the interpolation, it will give you better idea. Okay. So this will reveal the patterns, trends, and anomalies that might otherwise be missed. So you might like the same thing what I was trying to say. Like for instance, let's say this is a like a region, let's say somewhere in New Delhi or something. Okay, so you have some information regarding the rainfall in this area. So some rainfall data from here it was obtained, somewhere from here it was obtained, somewhere from here, and then somewhere from here, something like that. Using these data set, we can actually interpolate and get the information about the rain in other regions also. And this might actually tell you some patterns or trends or anomalies that are involved, which if you didn't do interpolation, you might not have understood. So interpolation kind of accounts for all those things. Spatial, therefore, the definition, like the proper definition for spatial interpolation is given as the procedure of estimating the value of properties at unsampled sites within the area covered by existing observations. The same thing that I was trying to say. Like you already have information about, let's say, 5 points in this area. And then using these 5 points, you're getting additional information. So with that, you might be able to generate some kind of pattern or something like that regarding that rainfall in that area or something of such sort. So that is more useful rather than just getting information about only 5 points. So interpolation will predict the values for cells in a raster from a limited number of sample data points. The same thing that I was trying to say. So it can be used to predict unknown values. That's what they were saying, unsampled sites, for any geographic point data like elevation case or rainfall, chemical concentration, noise level. So what the benefit of interpolation is that you don't have to go to this place, like each and every place, to get all the information. If you like before you plan for the survey or something, let's say you take a look at the area, you decide some points, which strategic points you can say. Like it's not like randomly you're going and collecting. Some strategic points you will choose according to your requirement and things like that. Then using the data generated from those points, we will interpolate. So like for example, in case of elevation, like you are going in a mountain area or like a hilly region, it's not possible to take data from every little point in that hilly terrain in order to account for the elevation. So we'll just strategically sample some sites. According to that, the entire region's elevation map can be generated if you are able to do the spatial interpolation. So the rationale behind spatial interpolation is the observation that points close together in space are more likely to have similar value points than points which are far apart. This is Tobler's law of geography. It's like, how do you say? Like you have a hilly terrain, something like this, something like this. So if you can sample 2 points from here and then something like this, so the point next to it will more or less have similar values. Like it's not exact same value, but you can estimate it to have a similar value. So this is Tobler's law of geography. So the rationale, this is the idea behind spatial interpolation. Adjacent points might be very similar, so it's not required for you to for ease of getting information, using the information. So it's not necessary that you have to be present everywhere. So this was one example that was given. So we have several points, like here you have 1, 2, 3, 4. I'm just randomly counting it and showing. It's not like this is the designated value. So we have 7 points, okay? Over here we have 7 points. So they are just randomly, like if you just look at this image, they're just randomly distributed in space. You don't have any other idea. You just know this is 14, this is 20, this is 20. Here we have 27, 30, like that. You don't have any other idea regarding this. Now what we are doing is using these 7 points, we are doing the spatial interpolation. We can create a surface, or we are predicting the values for each of the cells. Like if you make it into grids, for each cell there is a prediction. So instead of like here like for instance we have this 14 is basically, it is kept over here, okay? This is the 14, this is the 20, this is 24, this is 16, 30. This is slightly in the same line, that is the reason why it's not pushed up. So this is 27 and then this is 20. So these are the 7 points, that random points we saw in this image. But when it was done, like spatial interpolation in this grid format was done, so now they have proper places, and if you here you can see also. So here you can see like near 14 you more or less have 14, 14, 14. Here we have 16. So it's like it's automatically done mostly, like using some mathematical things, and that's how it is, interpolation is done. So for if at all this is signifying the elevation of some region or something like that, so the lesser the value, the lower the elevation, higher the value, higher the elevation, like that. What it can be any kind of data. It's not, I just gave an example as elevation, but it need not be just elevation. Then another topic that you need to know is the uh, surface representation. So as I was saying, like this interpolation that is mostly used like to help in the spatial decision making process, like as I was saying, terrain analysis, hydrology, mineral prospecting, hydrocarbon exploration. So like uh, even for military people and all, or for somebody who is exploring a region for minerals or something like that. So in order to understand the terrain, mineral prospecting, all those things, we can do the spatial interpolation. Now, we need to also have an idea about surface representation. So, what surfaces are like we exploring? So, before we go in further detail regarding the different interpolation techniques, there are differences in the methods which are used to surface representation. So, we'll be going through that first. Okay. So each surface representation is for a particular spatial scenario. Like for example, that's what we have mentioned. Like if you are looking at the Himalayan region and the Indo-Gangetic plains, Himalaya region is completely of mountains and like highs and lows, all those things. But Indo-Gangetic plain is more or less a plain. Like you might have certain undulations, but it's not very prominent compared to the Himalayan region. It's like Himalaya is more complex when compared to the Indo-Gangetic plains. So my this interpolation techniques that we use will be different. Like uh, it's basically like we may not have to use the same interpolation technique for both these regions, because Himalayan is a little more complicated, so the interpolation technique will be different for that. That same technique need not be used for Indo-Gangetic plains, because here you might have a lot of redundancy, like a repetition of data might be there, so it's a little more easier. So a grid representation of a surface is a functional surface. Okay, of any surface like you're taking, the grid representation is the functional surface, because you have a for every xy location it will also store a single z value as opposed to multiple z value. It's more like the aggregate point kind of thing. So maybe in a single grid itself there might be a possibility of different z values, but when you give this functional surface representation, we will only store a single z value. Therefore, these functional surfaces will be continuous in nature. So, functional surfaces are used to represent terrestrial surfaces that depict the Earth's surface, like these mountains and plains. Statistical surfaces that describe demographic, like population, things like that, pollution, population, things like that. Then mathematical surfaces that are based on arithmetic expressions. That is a mathematical approach. So that is how surfaces, functional surfaces are considered. Surface representation in its simplest form is done by storing x, y and z values that define the location of a sample. So like we have these, I hope you might be familiar with the idea of contours or iso lines. So that's like you might have seen the contour map, okay? So something like this. You can see like this. It looks something like this. So it's like one common characteristic will be there. For instance, this might be elevation thing. I'll see if I can show it on Google Map. Just a moment. It might be present. Let me try to show it to you. I have to change the terrain feature, I think. It's easier on Google Map, I think. I'm not sure how. Some elevated regions, if we take. Just let me just check. Please give me a few minutes. Okay, I'm sorry. I think in Google Earth it's not available. Mm. Yeah, I think in Google Map only we'll get it. And I was just checking it. So in Google Earth that's not available. In Google Map, let me see. Here you can see. Oh, it was showing again. It went. Okay, huh. Okay, I think here it's visible, right? So here you can see 200 meter is written, 300 meter is written. Maybe if I just zoom it out a little, it might show other features or some other terrain. I'll try to. Some hilly terrain, if I take it, I think it will be easier for you to understand. I mean, you might already be familiar. I'm just showing it so that the visual image is there. Whenever you are learning this GIS part, it's always better if you take a look at, I mean, have a little practical experience also. It's easier for you to understand rather than learning all these theoretical part. I'll also, as I said, I'll also show it in one of the sessions. It's just that it will take a little time to show all these things, and I didn't want to miss out on any questions or topics because of that. That's why in one of the sessions I'll definitely show. I think these are all part of contour lines. Here you can see 300 meter, 300 meter. Yeah, so that's just to give an idea of these things. So technically contour lines will join locations of equal value to each other. So this is how surface representation can be done. It can be done in terms of points. It can be done in terms of contours. It can be shown in terms of tints. If you remember triangulated irregular networks, then you have it in terms of grids also. If you zoom in, you can see the small, small grids that are present here. So this is, I think, representative of like these point data, like sir has also mentioned that, like for, if you're considering this as elevation value, okay, so systematically we are getting these point data, then we have elevation value. So according to the elevation value, like similar, here we don't have any much information, but then from these points we are developing the contours using the similar values like elevation values. So we created the elevation contours over here. So using these elevation values, we'll create contours. Then we'll fill in between wherever it is missing, and using the same point data, we can also create tin like here, which that you can see here, and the same point data, we can also create the grid that is like the raster image that you've got here. So just with this point data, not much information is present, but then using that we can actually generate contours, tins and grids. So why do we have to interpolate this raster data? That is important, right? So visiting every location in a study area to measure the height, magnitude or concentration of a particular phenomena, that's not very feasible. It's going to be difficult and it's going to be expensive. You can't go to each and every point. So instead what we'll do is we'll develop a strategy where we strategically dispersed sample input point locations are considered, they're selected and a predicted value can be assigned to all other locations. Okay, so certain regions you have to choose. That is why we are saying the strategy needs to be good, like where you're going to do the sampling, so that the unsampled sites will also be more representative of these that their region from nearby the sampling sites. Input points can be either randomly or regularly spaced, containing height, concentration, or magnitude measurements. Mostly, we prefer systematic sampling, but then that's not always possible. So, at least depending on what information that you are trying to gather, so according to that, you have to uh, prepare an idea of where you're going to sample, and if that those areas that you're sampling can also give you information regarding the unsampled sites. So as the toddler's law we were saying, so like close together, the things that are close together will have a tendency to have similar characteristics. So for example, like mm, an example that was given in the presentation also was like if it's raining in your area, okay, in your street it is raining. So at least in the nearby street, if it's not a very rare phenomena, it's going to be raining. So such things. So we have a little bit of confidence that okay, if I have the data for this particular street, that can account for the data for the adjacent street. It's not like we are considering one data, like for instance, this is one street, like uh, data from one street. Adjacent street is just like not very far away, and then we have another street which is really far away. This point can only account for this one. If you consider, do the interpolation for this, then it might not be very accurate. So that's why I was saying like the strategic sampling is very much required for a proper interpolation. Input points can be either randomly or regularly spaced. That's okay. Like if you can do systematic sampling, that's well and good. But if it's not possible, random or regularly spaced points are also fine. But that needs to be done properly. Then there are different interpolation techniques that were discussed. So we'll also just touch upon the topics, just refresh your memory. So global versus local interpolation. So global interpolators determine a single function which is mapped across the whole region. So a good example is the trend surfaces, which is one type of interpolation technique. This is a tech like IDW trend surfaces, all interpolation techniques. Okay. So whereas in case of local that interpolators, they apply an algorithm repeatedly to a small portion of the total set of points. This is a little more, what do you say? It's for a bigger uh, region, a whole region, and this is like for a more localized uh, interpolation. Like when we do it or when we discuss this trend surface IDW in detail, maybe you will be able to understand better. Then we have exact versus approximate. So exact interpolators, they will honor the input data points, which doesn't mean that the surface is exact. So the approximate interpolators, they will allow for uncertainty in the input data points, which allows for smoothing. So this is like exact interpolators, like you have given this input data. It may not be very correct, but then they will consider it as an exact data point. So exact, like that is an exact one, so accordingly they will interpolate. But approximate interpolators will always consider an uncertainty, like it might vary. There is a possibility for a difference. So according to that, you can actually do the smoothing process. Then stochastic versus deterministic interpolators. So stochastic methods incorporate the concept of randomness, similar to linear regression model or best fit model, like that. Deterministic methods will not use the deterministic, the name itself tells you probability is not considered, it's more or less definite. Then we have abrupt versus smooth. Abrupt interpolators allow for barriers like the faults that are present on the earth's surface. So such abrupt change will be considered in case of abrupt interpolators, but smooth interpolators will only make it like this. They will not account for this shift. This might be the actual one, but if smooth interpolation is done, we know that this is there, we know that this is there, so we'll just combine it, but we will not account for this offset. Then this linear interpolation, which we are very familiar with mostly, like you might have also done that. Like there are two types of interpolation. We have the linear interpolation, we have the non-linear interpolation based on mathematical function. Okay. So here we have an example for the linear. So we have this 100 feet, then 110, 120, 130, 140, 150, like that. Okay. So between this 130 and 140, that's why it's a question mark is kept here. If I want to figure out what value is there, it's very easy to predict how it is going, right? Based on this trend, exactly in between, it will be like 135 probably. Here it will be 105. So that prediction is possible because we have this trend that is established over here. So surface is changing in a linear fashion. So simple mathematical functions itself is sufficient to do this linear interpolation. Then we have point-based interpolation that is used for data which can be collected at point locations. Okay, like weather station readings. I don't know if you have seen it on video or something. So people install such things like we have weather station readings for determining the wind, the precipitation, all those things. So that thing, spot height, soil and groundwater level, these are like point locations. So exact methods of point-based interpolation is also known as Thies and polygons. This is mainly like one good application is for this groundwater level. So these polygons, they basically assume that any unknown value within a polygon is best represented by the sample point inside that polygon. Like you have a polygon like this. So any unknown value will be accounted for by this aggregate point, you can say. So this creates a discrete interpolation method, meaning the value does not gradually change between points but instead shifts abruptly at polygon boundaries. We don't have multiple information here. So at polygon boundaries, over here it might be an entirely different value. It will not be a continuous change. This is point-based interpolation, and mainly like practical example that I know of, there are other examples also, but mainly I know of is the groundwater one. So in GIS, it is used for weather mapping. So assigning rainfall data from weather stations to surrounding areas, because we'll be having weather station in one point, right? But then that we have to interpolate for the surrounding region. That's how it is done. Then hydrology, dividing watersheds based on nearest stream flow measurement points. In agriculture, estimating soil properties based on scattered soil sample locations. So all this is helpful when we are dealing with a huge region and it's not possible to sample every nook and corner. So in such cases, this interpolation is very useful. Now we'll be discussing the problems mainly because you already have received a solution for week 3 and week 4. So I thought we'll just review that. If the solutions were not given, then it's not possible to discuss. So since it's already there, we'll discuss that. So in georeferencing, if a user chooses third order polynomial equation, the minimum number of required GCPs are, actually I've already given the diagram here so it's easier for you, but you can just do the calculation and tell me if that's possible. Like you're familiar with the idea of ground control points, right? So the minimum number of ground control points that are required if the user is using a third order polynomial. Sorry, I think the animation worked ulta. Sorry. Anyway, the answer is 10 because see, this is the formula that is used. P plus 1 into P plus 2 by 2. So we have P as 3. So it is like 3 plus 1 into 3 plus 2 divided by 2. That is like 4 into 5, that is 20. So 20 by 2, which is 10. That is what is given here. So for third order polynomial, the number of GCPs required is 10. But then, as Professor Seraph has also said, it's always better if you take thrice of that. For instance, for first order, 3 are required, they say, but then multiply by 3, you take 9. In this case, you take 18. So like with that's what I'm saying. Theoretically this is possible, but with practical experience, they they're saying that you just have to take thrice of that. So in place of 10 you might have to take 30. In georeferencing, the Y scale is dash because the origins of an image and a geographic coordinate system are different. The origins are different for an image and a geographic coordinate system. So because of which the Y scale will be what? Positive, negative, square root, or none of the above. You must be already knowing this since you have submitted the assignment. I'm just refreshing it. Okay, so the answer is negative. Why? Because the origin of image, in case of image, we consider it as from the top left corner. Okay, so like you have an image over here. So its origin is considered from the top left corner. While if you have a geographic coordinate system, its origin is considered from the, okay, it's considered from the bottom left corner. So it's like just the opposite. So because of that, these questions are there in the assignment, I think. I took it from your assignment only. If not, I think this will be useful also for you, like for while you're preparing for your examination. Anyway, I'll be uploading these slides so you can go through this. But I think I've directly taken it from week 3 and week 4 assignment. Anyway, like consider this as practice questions, so it's easier to understand the concepts that you have learned. So yeah, as I was saying, origin of image is from the top left corner, while for the geographic coordinate system, it is from the bottom left corner. So because of this, the y will be kept as 0 and it will be, y scale will be negative. Relatively, Quadtree's raster data compression technique provides what level of compression? Like we know different types of compression, right? So amongst all that, what kind of compression do we get from Quadtrees? See, there is one thing like we can only, yeah, I understand. See, we were instructed that like you need to have a little more practice with the problem solving, right? So we were given the instruction that when you get these assignments on the NPTEL platform, so unless and until that deadline is over and they have already provided you with a solution, we should not be discussing those questions because you are supposed to submit it before. So that's why we don't discuss it at the time. Then when it is done, then we are discussing it. So I don't know if there is a difference in the questions that you guys are seeing and the one that I'm seeing. But anyway, like as you said, like it'll be an addition if it's new to you. It'll be helpful also. Thank you for informing me anyway. I didn't know that. So yeah, relatively Quadtrees will provide high compression, good compression, because here we are actually If you remember from the previous sessions, if you have multiple grids like this, and you're basically dividing it into four quadrants first, then according to the requirement we'll be further dividing it, so it gives you high level of compression. Mr. Sid raster data compression technique can provide compression up to uh, what kind of ratio? Yeah, it's possible that it might be previous material. Yeah, that's also possible. So, do you know the answer for this question? Like Mr. Sid raster data, that is one type of lossless data compression technique. So, how much of compression is possible, known to be possible with this technique? Not exactly. Like it can even go up to C. Yeah, 50 is to 1. Like that is possible. Like 50 is to 1 compression is possible. So it's basically like if you have an image which is like 50 MB, then that can be compressed to 1 MB depending upon the redundancy, that is repetitiveness that is present within the image. During data generalization, number of nodes of a polyline or polygon are, like what is done during data generalization to the number of nodes. Just have to think what data generalization is, then the answer is there. What happens during data generalization? Like what exactly do we do for, like when we are doing the generalization? The answer is reduced, because see, we are generalizing the data, so we don't need multiple data sets which might be very similar to each other. So we'll be sort of generalizing it, therefore the number of nodes will be reduced. We might have a more representative node for, maybe let's say like 5 nodes are there, so one node will be more representative of the all the 5. What does the abbreviation RDBMS stand for? This is very easy because only one answer is there. Yeah, Relational Database Management System. In which database tables are related by sharing common entity characteristics? Again, it's easy. Okay. Common entity characteristics means something is related. So the answer is relational only. Yeah. The advantage of standard query language in relation to GIS databases. See, here we are considering those ones which have similar, as the question itself is showing, we have common entity characteristics. So we are considering those ones which are related to each other. So in such cases, we will be using the relational database tables. Networking, I think, I'm not very sure. It might be, uh, did you give the answer for the next question? Ah, okay, okay, fine. Okay, fine. I'm not very certain about this networking thing. Maybe I'll check that and tell you. But the idea is that the entity characteristics which are common, in such cases, from that itself, you can understand it is like relational database tables, something which is related. The answer is correct for this question. So it is good at handling geographical concepts. So many SQL databases support spatial data types like point, line, polygon, geometry, geography, all those things. So geographical concepts basically. Point means you get latitude, longitude. Lines, we get sequence of points with latitude, longitude data. Polygon also similar thing. Country borders and all considered in polygons. The measurement technique which uses 2D Cartesian mathematics to calculate lengths and areas is called. Just have to focus on the term 2D, then you will get the answer. Yeah, the answer is planar because we are only considering, no, it's planar because we are considering 2D Cartesian mathematics, no? In length and area, we were discussing that. The answer is planar. Generally, all area measurements calculated are, again a similar question only. In area and line measurements, yeah, we have to consider, like always we associate it with planar measurements or 2D. So its answer is planar. Basic GIS functions are area and distance measurement, buffer generation, reclassification, all of the above. Yes, the answer is D. That is all of the above. Basic spatial analysis involves, when you do spatial analysis, what? Yeah, you're right. We have both attribute queries and spatial queries, like non-spatial and spatial queries will be there. Yeah, you guys are right. What is a model? This from the beginning itself we were discussing it. Yes, it's a simplification of reality. It may not be the exact, 100% representation, but then it is a simplified version of the real world. Like that is what we do in GIS, okay? It's not exactly an instruction to GIS. Model is more or less what we get after giving the instructions, like whatever process you're doing, no? Pre-processing, processing. So whatever result that you're getting, that is the model, and that gives you a simplified real world representation. It's not just about storing spatial data also. Yeah, it's not like it's a kind of an inclusive thing. Like all these things that you're doing, no, like spatial analysis, non-spatial data, all these things included will give you the model. Yes. Points close together in space are more likely to have similar values than points farther apart. This we had just discussed. Which law is it? While discussing interpolation, we were talking about this. Is Tobler's law of geography. Okay, so the answer is C, which is Tobler's law of geography, which tells you that points close together in space are more likely to have similar values than points which are farther apart. Which of the following spatial interpolation techniques is an example of a local, exact, abrupt, and deterministic interpolator? Actually, I have not discussed this in detail. So, this I was actually putting it for the next class because we had too much information. But if you know, you can just let me, like you can tell. Like A, B, C, D, they are all interpolation techniques. No, the answer is Thiessen polygon. But that I'll discuss in detail in maybe Thiessen polygon also. I'll try to show an example. I'll try to show it in the next class. Then maybe it's more understandable. Spatial interpolation is the procedure of estimating the value of properties at. This is the basic essence of spatial interpolation. So you can just look at the options and then let me know. No, like read the question very clearly. Like you are estimate. It's the procedure of estimating the values of properties at where. Where is the estimation done? And sample sites. Yeah. No, not sample size. Sample size, you don't have to do estimation. You already have the value. Using those sample like information from the sample sites, we are estimating for the unsampled sites. Pre-processing in GIS involves the following. Just yeah. It involves format conversion, generalization, merging. Not just this, we also discussed other things, but out of these options, these are the like all these three are part of pre-processing in GIS. The following are also part of processing. Pre-processing and processing are two different entire processes. Like yeah, it's different. Not exactly, like all these things we are doing in pre-processing only, like even georeferencing also. Like if you georeferencing, interpolation, image interpretation, all these things we are doing part of pre-processing. Like if you're getting an image, you have to, without giving it these geographical representation, we'll not understand, we'll not be able to proceed further. So for that purpose, you have to do georeferencing. Then you have some data points within that image, you have to do interpolation. Then you have to do image interpretation. So all these things are actually not part of processing, but rather somewhere in the pre-processing and somewhere in between. But it's not part of processing. One type of image fusion or merging technique is based on. This also, I think I'm yet to discuss in detail, but you can just give it a try. Just color transformation. Like if you remember, we had merged the image like that FCC, false color composite, and panchromatic. So in that, uh, that color transformation is done. So that is one of the thing. Image transformation, I'm also a bit doubtful why it's not considered. Maybe I'll check that. I was thinking it will be image, but yeah, I'll check that and I'll inform you. Reclassification involves the selection and presentation of a selected layer of data based on the classes or values of a specific what? Like reclassification, only like one thing you have to bear in mind is like, for example, you have an image showing elevations ranging from 0 to let's say 1000 meter. Okay. So when you do reclassification, you can actually sort of make it like 0 to 100, 100 to 200, 200 to 300, like that till 1000. So that kind of reclassification can be done. So like the selection and presentation of a selected layer of data based on the classes or values of a specific what, like using what can we do this. The answer is attribute. Like you have this attribute table, no? So you have the information. For instance, like the one I was saying, like elevation details, it might be there in the attribute table. It might not be a spatial data. So that using that you can actually do the reclassification, or maybe some population thing. So that also you can do reclassification. So attribute is the one that you're actually uh, sort of selecting and presenting. So that's the questions that I had with me. So is there anything else? I have basically just touched upon the topics today because, as I said, there is a lot of information available and I didn't want to waste your time discussing each and everything. You might have already gone through it. Yeah, thank you, Rahul. So if you don't have any further questions, we can end today's session.